Hello everyone. So, we have reached almost at the end of this course evaluation of textile material. In the last class we have discussed the bending related characteristics and how to measure the bending behavior of textile material, and cantilever principle is the most popular, most widely used principle, and if the fabric is very flexible like knitted fabric, and we have mentioned we can use other methods of measurement, that is a heart loop method, ring loop method and pier loop method, as we have already discussed, for limpy fabric like loose knitted fabric, and L is the length of strip, L 0 we have discussed, it is undistorted length of loop, that is the distance between grip and the farthest point, and after hanging on its own weight, the distance there will be some distortion and that distance becomes L is more than L 0, and the deflection, that is the stiffness, is calculated based on the difference d is L minus L 0, as we have discussed, and this for ring loop L 0 is nothing but that is the distance from one point to another point, grip point to, that is nothing but a diameter, okay, diameter of the loop, and which is L by pi. So, this is the way we can express, okay. And from by if we know the L 0 value and if we know the deflection d, the difference, then we can calculate the bending length using this formula, where function of theta is L cos theta by tan theta to the power 1/3. So, here using this function of theta for a theta equal to, here in case of loop ring loop, the theta is 157 multiplied by d by L 0, and if we know this value deflects, only we should know the deflection. If we know the deflection value, as in the last class we have mentioned, and we can calculate the bending length. Okay. Similarly, for pier loop, if we know the deflection, only the deflection, and function of theta is same here, and then we can calculate the bending length. Similarly, for heart loop, okay, using this formula. Okay. Now, the next characteristics is shear characteristics. Now, shear is a characteristics which is unique for textile material. We can actually incorporate all other characteristics in any flexible material. So, it is the most important property which determines how the fabric will perform when subject to wide variety of complex deformation during use. Suppose my cloth, my shirt, when I actually move the fabric, the characteristics of the fabric is that it changes the shape according to my body movement. So, that makes my actually feeling it is comfortable. Otherwise, what will happen? The ability of a fabric to deform by shearing, it differentiate from other thin material. So, that fabric's characteristics, its only uniqueness is that it is flexible and it has got less shear stress. Okay. So, it can deform easily by shear. That means, whether it is a woven or not knitted, suppose these are the warp yarn, okay. So, weft yarn and these are warp yarn. Now, when we deform, when we apply force, okay, these yarns will get deform very easily, there will be, because there is no actually positive binding. So, they will deform easily due to its inherent structure. Now, if it is asked, instead of textile material, instead of say woven fabric or knitted fabric, we use any polythene sheet. So, for any polythene sheet, we can incorporate any characteristics. Suppose if you ask the polythene sheet in, if I am making a shirt from a polythene sheet, you may ask, it is not, say it is not permeable. So, I can incorporate permeability by punching the holes. Okay. Then one may ask that it is not that flexible. I can definitely have a polythene sheet with high flexibility. Even we can incorporate absorbency, we can incorporate everything, we can incorporate, but one thing we cannot incorporate, its shear characteristics, because the polythene sheet, any other thin sheet material, even very flexible sheet material, if we make if we prepare our clothing, that will have some other characteristics, but it will not be able to actually deform according to my body movement. So, that makes the textile material unique. Okay. So, that is the characteristic which is known as shear characteristics. So, it does not conform, those other sheet material does not conform to the contour of the human body, and that textile material only do that. So, it is difficult to measure. So, shear characteristics is very difficult to measure, because it is flexible. For any sheet material, shear characteristics measurement, it is not that difficult. Okay. It is basically when, suppose there is a material, any other material, stiff material, and we are gripping in, this is the one grip point, okay, the material we are gripping. Now, we will apply one force. So, with this which is parallel to the base, okay, and with this force, if there is any deformation, suppose this is the deformation, it is deformed, then we can measure the shear character, this theta, the tan of this theta, tan theta is the shear strain, and we can measure the force to deform. So, then you can calculate the shear stress. So, but for textile material, as it is very flexible, this type of measurement is very difficult. Okay. Now, so this is the simple shear. For a simple shear, parallel stress F is actually acting in opposite direction, that this may be horizontal direction or may be vertical direction, and where we can measure the deformation, angle of deformation theta, and tan theta is shear strain and F is shear stress. Here assumption is that the initial, that area of rectangular shape, okay, material, the after deformation the area is same. So, here the G is the shear modulus, we can calculate by the ratio of shear stress and shear strain. The G is nothing but the ratio of F by tan theta, but the main problem is with the textile material, and to test shear characteristics of textile material, we have to we will use the same principle, but we will modify the setup. The modification here is that if any textile material, if we try to shear, before shear, due to its high flexibility, this fabric will buckle, this buckling will take place. So, that buckling, just to avoid this buckling, prevent this buckling, one vertical force is applied, extra vertical force W is applied. So, that the width wise there is no buckling, this becomes straight. So, that extra force we have to apply in addition to F, we have to apply an extra force just to have the W, just to actually balance the W, we have to apply extra force F dash, which is equal to W tan theta, when tan theta is the angle of shear, and this force is due to W, and then the force required for only shear the fabric we can calculate by subtracting this W tan theta from total force required F. So, this will be F minus W tan theta, which is basically required to shear the fabric, and this stress is expressed in terms of force per unit length of the fabric. So, if this is the length and we can calculate. Now, what is shear hysteresis? Now, shear hysteresis is that, so suppose this is a fabric initial stage. Here at the initial stage, although there is no positive binding, but the fabric to, so yarn to yarn, the warp yarn to weft yarn, this yarn to yarn friction will be there. Okay. This the shear force when it is actually deformed, there will be frictional sliding. That means, suppose this is the force and what we are doing, we are trying to deform. Okay. Now, this due to that frictional sliding, we need some force. So, that is called, that is a shear stress, we need shear stress just to have some frictional sliding between the yarn. Okay. The yarn will, this is this initial form, and after that this will actually, this is in this sheared form. Okay. Now, that is how it is. So, this is a shear strain and here it is a shear stress, shear stress. Okay. Now, this is okay. After that, and we can calculate the shear modulus and other. Now, when once it is coming back, suppose after that deformation, it's we are again trying to come back. So, in that case, when it is shearing, when it is coming back, it will not follow the same path. Here we have to have, this will follow a different path due to the frictional locking of the this yarn. Okay. Now, here this is the, and this difference is known as the shear hysteresis. Now, the hysteresis occurred due to frictional force at the intersection point of warp and weft. Okay. Now, where it is going and then it will come back, and from this point again if we want to have without any too much the shear strain, we have to apply certain force. Okay. That is how it is, the curve is like this. The initial shear modulus is that shear, that slope at the initial points. If we take the slope, measure the slope, that is the initial shear modulus. Shear modulus at 0 shear angle, what is that? At 0 shear angle, what is the shear modulus? So, the slope at point B and at point D, if we take the slopes, so we will get the shear modulus, there will be two values. So, this will be the slope at the shear at 0 point. So, these two values we can take the mean of this, and also hysteresis at 0 shear angle. So, the difference between B, the distance between B and D, it is the hysteresis. So, from there we can calculate the shear hysteresis, and which is basically due to the frictional contact. Now, shear can also be measured by biased extension. So, this technique, this principle is used in fast instruments. Okay. And the principle here is that we cut the fabric in the biased direction, not in along the warp or weft, we cut the fabric in 45-degree bias direction with warp. Okay. Now, we will use this equation which is 1 by G equal to 1 by E 45, sorry 4 by E 45 minus 1 by this sigma 2 by E 1 minus 1 by sigma 1 by E 2. So, what are these values? G is the shear modulus of the fabric and E 45 is the Young's modulus at 45 degree. That means, at 45 degree, suppose this is the fabric, at warp wise there will be certain Young's modulus, because the yarns are at parallel condition, there will be high Young's modulus. At weft direction also it will be higher, because yarns are parallel, but once we measure the shear modulus at say Young's modulus at certain angle, that means at 45-degree angle, the threads will have very less modulus, because it will deform very easily. So, that is why E 40 and E 1 and E 2 are the Young's modulus in warp and weft direction. Now, if we see and that sigma 1 and sigma 2, these are the Poisson's ratio in warp direction and weft direction. So, the relationship is between the shear modulus, the biased angle Young's modulus E 45, E 1 and E 2, and if we see that here the E 1 and E 2 will be much higher than E 45. So, that is modulus at biased direction is it is very less, because the threads will simply actually take their action, because the shear stress is less. Okay. That is why in these equations, as E 1 and E 2 are very high, the initial we can eliminate this, for simplicity we can eliminate these terms, the second and third term in the equation. The equation will be simplified for all practical purpose, we can use this, that will be 1 by G equal to 4 by E 45, that is E for the G equal to E 45 by 4. If we can measure the Young's modulus at 45-degree angle and divided by 4, we will get the shear modulus. So, this is the equation. So, E 45 is equal to almost equal to 4 G. Okay. So, the sigma 1 sigma 2 are the Poisson's ratio, and here we can calculate the the shear modulus of the fabric, and the shear strain tan theta is related in the fashion like 2 E plus E square, where E is the biased extension by the force T. If we apply T force and then we will have the biased extension. So, that is tan theta you can measure. So, where it is infinitesimal, it is very small, okay, infinitesimal strain. So, that is E is very small. If we take the E as a very small value, this E square will be small. So, that E square we can actually eliminate. So, this will be tan theta almost equal to 2 E. Okay. So, this value is 2 tan theta 2 E. So, if we measure the E biased extension value, so we can calculate the tan theta, and F by 2 tensile force. So, that is tensile force by 2, which is the effective shear force. So, that shear force and shear strain we can calculate using this formula for very small deformation. If we deform at higher value, then there will be other this equations will not be actually valid. Now, we will discuss another characteristics as I have mentioned, which is actually linked with the shear and the bending characteristics, okay, and which is drape. And the drape, the term used to describe the way a fabric hangs under its own weight. So, if we hang the fabric, this fabric under its own weight, how the fabric will get actually will hang, will make some profile that shows the drape characteristics, and it determines how good a garment will look like. So, it is not only the garment, for any other fabric like curtains or any other fabric which actually requires a fall, and that appearance is actually dependent on drape characteristics, and it differs from fabric to fabric and depends on the end use, which is important. The drape, like strength, textile material with higher strength means it is a better, like uniformity, which is more uniformity it is better, that means CB percent or U percent, lower U percent is better. But here in drape we cannot tell that higher drape coefficient, higher drape value is better or not. Okay. So, that depends on the end use. Drape coefficient or drape value is just an indication, we cannot tell the whether the fabric is good or bad, that depends on the end use of the fabric. Once we need the stiffer fabric, that means the drape will be different, will be high drape, and if we need a flexible fabric, that will be lower drape. So, we cannot compare the value, okay. We cannot tell that higher drape value is always good. A particular value cannot be classified as either good or bad. So, it depends on the end use, like this is the drape, okay. It is a multi-directional curvature which is formed, okay, and which depends on shear and bending property, and if we take these two properties together, then it forms a drape, and which shows it is a look, how pleasant the fall of the fabric will be. Now, the measurement is done by using the drape meter, where this is the fabric, okay, fabric specimen without any with its normal circular fabric specimen. A1 is the total area of the specimen, okay. We have cut the fabric, and as it is flexible, once we are placing the fabric with on a support disc of a certain known area A2, then what will happen, on its own mass the fabric will start hanging, the fabric will hang, and the projected area, we can whatever projected area, this is the this circle is the actual area of fabric A1, A2 is the support disc, and once we are hanging, this will make a projection. This A3 is the shaded portion, is the total projected, the projection total shadow area by draped fabric, okay. And the projected area is that A3 minus A2, A3 minus A2 is the which is actually projected from the support disc, okay. And then if we know all these values, because A1 is known because we cut the fabric, A3 is A2 is known because we know the area of the support disc. Only thing is that we have to calculate, we have to measure the area of this area of this shadow, and if we know that, then we can calculate the drape coefficient. Drape coefficient D is A3 minus A2, A3 minus A2 means projected area divided by A1 minus A2, that means the difference between the area, difference of area between the actual fabric and the support disc. So, if we know these values, and then we can calculate the drape coefficient. Now, as the fabric gets stiffer, the drape coefficient will be high. Suppose a fabric with a which is totally lumpy, it does not have any projected area. So, what will happen? The projected area, that means A3 will be equal to A2. Okay? A3 will be equal to A2. In that case, so that this portion, this A3 minus A2 will be 0. So, the drape coefficient for that fabric will be 0. Now, in place of fabric, suppose we use cardboard. Okay. Cardboard means that A3 will be equal to A1. Okay. A3 will be equal to A1 because there is no drape at all. So, A3 is equal. So, A1 is A3 is replaced by A1. In that case, if we see numerator and denominator become same. So, D value will be 1. So, that means the for any practical purpose, the drape value it is ranging from 0 to 1. For totally stiff fabric it is 1, for totally lumpy fabric it is a 0. Okay. So, that way we can have, knowing the drape coefficient value, we can actually come to know whether the fabric is stiffer or not. Okay. Now, let us see the principle of this instrument. Here actually from top light beam is falling, and if we calculate, and this is the type of shadow, at the bottom there is a shadow. This shadow we can trace, and if we can measure the area, and that area is actually from that area we can calculate the drape coefficient. Now, the area measurement sometime it is very difficult. So, that if we can trace and we can cut the fabric and we take the mass, and if we know the actual mass per unit area of the paper, that from that we can calculate the area of the projected portion. Now, if we see the animation here, this is the support disc. Okay. The step on when there is no fabric, okay, and then we are trying to get the shadow of this support disc. This is the shadow of the support disc, okay, that we know. Next is that the hanging the fabric, we are now placing the fabric on it. We are placing the fabric, fabric is hanging, and now we are getting the shadow of the fabric. Shadow of the fabric, and we are calculating the drape coefficient. Now, main problem with this system is that the light which is actually diverging, and actual area whatever we are getting, it is not the actual area of the fabric projected area, it has been actually enlarged. This area is enlarged. So, that is why sometime this gives error value depending on the length or distance from the light source. Okay. And what we can do to eliminate this problem, we can have one system where light is not a diverging type, light will be projected just exactly in parallel beam of light will be projected, then we will get the exact value of the fabric area, and that is done by the Cusick drape tester. Okay. Cusick drape tester is that the shadow that the fabric cast is traced on a annular paper, where this is an annular paper and the shadow we actually whatever it is casting, it is the that shadow we are just cutting out. Now, this in this annular ring, this is paper of known mass per unit area. So, mass per unit area of the paper is constant and this inner its hole, this is the size of the support disc. This is the support disc size and this is the size of the fabric. Okay. The size of the fabric and the shadow shaded portion we can trace and we can simply cut, and then we can take the ratio, and mass of the whole paper ring is taken and the shadow part is then cut out and weighed. So, first the mass is taken, then shadow part is taken. Okay. Now, we will see and then let us compare with others earlier process. Now, if we take the mass of the whole paper, that means what we are trying to take A1 minus A2, A1 minus A2, that is denominator we have taken the total annular ring. Okay. And when we are taking the mass of the total shadow portion and this cut out this portion, the shaded portion, then what we are trying to take, it is a A3 minus A2. Okay. It is because this is the actual paper is annular, this is whole is there. So, this projected length, projected area we are taking, because the paper the mass per unit area is constant. So, the ratio of mass is showing the ratio of the area. So, here in this method, if we simply take the trace the shadow and take the mass, then it will be perfected, and this the annular ring size is exactly as the size of the fabric, because and size of the initial sample, and as the light beam is projected a parallel light beam. So, there is no divergence. So, there is no extent that the enlargement is not there. So, exact size is we can measure. Okay. Now, the principle is that the shadow that the fabric cast, okay, is traced on a annular paper. So, this is the annular paper is placed here above this here it is a the support plate, okay, support plate is here, and the this area the annular the diameter of this annular paper is equal to the area of this support plate. Okay. Now, the paper mass per unit area is constant, mass of the whole paper is taken and thin shadow part is cut out and weighed. Now, if we see the animation, and before that let me explain here. Now, the light source is at the bottom and here it is a parabolic mirror. Okay. It is a basically concave mirror is there, and from light source light is divergent, different source light divergent light is falling, and then it is basically its parallel light is being actually reflected, and once it is a parallel light is reflected, the this is the fabric profile and exact shadow of the fabric will be placed here. Okay. And this exact shadow the paper, the annular ring paper is placed on a glass support. So, why is it glass? Because it should be transparent, so that it can light passes through and shadow can be is visible, and we can simply trace. Okay. And there from there we can calculate the mass. Now, the light is actually falling, the fabric sample specimen is just behind the light, it is not direct light is falling. Now, it is getting reflected and parallel light is getting reflected. Okay. Now, as the light beams are exactly parallel, so that there is no divergence, the shadow we are getting here, we are tracing here, which is exact shadow of the fabric, and we take the difference ratio of the mass, we will get the drape coefficient, and expressed, we can express in terms of factor also, or we can express in terms of percent by multiplying by 100. And 3 different specimen diameters is recommended. Okay. When the fabric drape coefficient is very small, so less than 30%, 24 centimeter for very limpy fabric, okay. For medium fabric is 30 centimeter, and for stiffer fabric 36 centimeters. So, these are the various fabric sample diameters are given, and then the drape coefficient we can measure. Okay. And the last part is that there is a relationship, direct relationship, diagram shows the relationship between shear stiffness, drape coefficient, drape percent, and the bending length. Now, try to see one by one. Suppose a fabric is having 0 shear stiffness, this is the 0 shear stiffness. Okay. At 0 shear stiffness, if the fabric bending length, that is bending length means it is highly flexible, and the imaginary there is a 0 shear stiffness, there is a in that case the drape coefficient will be 0. So, there that means it will simply fall, as I have mentioned earlier, 0 drape coefficient. Now, for say 0 shear stiffness, if we increase the bending length, we are increasing the bending length, that means drape coefficient will increase. Now, how do we achieve this type of situation? Now, let us assume a situation where we have a fabric, we have made a fabric with say rods, highly polished, extremely polished rods we have placed, okay. And this there is no friction, there is a 0 friction, 0 friction between the rods. In that situation, imaginary, if we apply force, so there will be no shear stress. So, that will this will simply slide, there is no shear stiffness, but as the rods, there are rods. So, we can see, we can assume that rods are highly stiff, that means there is a infinite stiffness, that means it will never bend. Okay. So, bending stiffness is very high, but shear stiffness is very low. In that case, again the fabric will have 100% drape coefficient. Here the curve shows, this picture shows that the fabric with say high infinite bending length, that means very high bending length, and the shear stiffness, even if it is 0, if we take the y axis, then bending drape coefficient, as the bending rigidity increases from say 0 to infinite, okay, then the drape coefficient will gradually increase. Similarly, suppose bending length is 0, bending length is 0 means the fabric bends easily, very flexible, but if we increase the shear stiffness gradually, that means there is no movement, the movement we are blocking. So, we can assume a fabric with 0 bending length, highly flexible bending length, but their movement has been blocked Okay. So, if we take a fabric with a very flexible fabric, highly flexible fabric, okay, but what we are doing, we are actually knotting the this, we are actually, you can assume the fabric with highly flexible. So, there is no bending rigidity, very flexible fabric, but what we have done, we have put gums at each and every, we have joined, we have actually soldered this ends at this point. So, what will happen? This will not have any shear, okay. Shear stress will be high. So, in that case, but this fabric is highly flexible. So, in that case, the fabric will have certain values of the drape coefficient. So, that is how this graph shows here the shear stiffness, if we increase gradually, even if the bending length is 0, still the drape coefficient will increase. So, that means highly flexible fabric will not result the 0 very flexible, very good look, but very good fall. In addition to the flexibility, we have to incorporate the shear characteristics. If yarn cannot actually move past each other, then there will be higher drape coefficient. So, the problem here to calculate drape coefficient is that projected area of 30 centimeter diameter fabric specimen placed on 20 centimeter diameter support plate of drape tester is 302 centimeter square. Drape coefficient of fabric, what will be the drape coefficient? That means, what is the projected area? Projected area is means the shadow area minus the area of the support disc, that is the projected area. Drape coefficient is known and the projected area is given, which is nothing but A 3 minus A 2, A 3 minus A 2, this is given, okay. This is given, and A 1 is the fabric specimen, this 302, this is the 302 is the A 3 minus A 2, and diameter of fabric is given 30 and diameter of specimen holder is the 20. From there we can calculate the A 1 minus A 2. So, A 1 A 2 we can calculate. So, projected area A 3 minus A 2 is 302 directly given. Specimen area is calculated pi by 4 30 square, that is pi by 4 900 square centimeter, and area of support disc is calculated pi by 4 400 square centimeter, and from there we can calculate the drape coefficient is 302 divided by the difference in these two areas. So, the drape coefficient is coming out to be 0.769, that is 76.9% is the drape coefficient. And in addition to this, there are standard techniques, the total systems of measurement of objective assessment of fabric handle. So, there are two instruments, set of instruments are available, commercially available, okay, and those instruments, the set of instrument measures the low stress mechanical and surface characteristics of fabrics. These are the Kawabata evaluation system for fabrics, another is that fabric assurance by simple testing, and in this course we will not discuss the detailed analysis or details of these instruments, we will just mention, and you will learn in the higher course. There will be another course, that is the advanced testing of textile materials, that course it is these things will be discussed, and the principles are the correlation between the subjective assessment and corresponding mechanical measurable fabric properties are that the subjective assessment is the smoothness, firmness, fullness, crispness, hardness. These are the subjective assessments of the fabrics, and those can be correlated with the objective assessments, the low stress mechanical properties of fabrics. Okay. The tensile characteristics, tensile as shear characteristics, bending strength, bending not what we are doing here, we will not actually it is not the high load will not be applied, only the low stress mechanical characteristics will be evaluated here, and the compression and surface characteristics will be measured. And there are 4 modules in Kawabata system, KESF 1 or FB1 for measurement of tensile and shear characteristics, the model 2 for measuring the bending characteristics, model 3 measures the compressional characteristics, and model 4 which measures the surface roughness and friction characteristics. So, these 4 modules are there, and similarly the first fabric assurance by simple testing, which is developed by the CSIRO Australia, and there it gives the objective indication of fabric handle characteristics, and there are basically 3 series of 3 instruments and one test method. Instrument first one is compression meter, which measures the compressional characteristics of fabric, and second one is the bending characteristics of fabric, bending meter, which actually works in the same principle of the Shirley instrument we have explained here. First 3 measures the tensile and shear characteristics, okay, that is extension meter, and first 4 is nothing but one test method, which measures the dimensional stability of fabric and also hygral expansion. Okay. So, all this detail we will learn in other course, and with this we will finish this course of evaluation of textile material. And here we have discussed all the characteristics from starting from fiber, loose fiber, yarn, fabric, okay. And we have now come to know that different evaluation techniques and their implications, how to actually interpret all this data, okay, that we have discussed. Hope this course will help you in your understanding in evaluation of textile material, and till then, thank you.